Hi, and welcome to this video on converting equations back and forth. And this is conversion specifically for our polar mode to Cartesian or Cartesian to polar. So this is used specifically in this calculus series, but could be perhaps in a pre-calculus course as well when you're doing these conversions. And what is important to note, or at least what I think is important to note here, is that all of the things in the box are things that we know just from a basic right triangle here. So if I have some theta, and if I name my sides so that x is the horizontal here and y is the vertical, and I will name r that hypotenuse, we know the Pythagorean theorem exists, so that's that relationship right there. We also know that if I was given x and y, so that's what allows us to find the r, we also know that if I'm given x and y, I can use tangent to find theta, because that is opposite, right, over adjacent. And then the x and y, so if I was given r and theta, so if I'm given that and that, we can find x and y by also using trigonometric ratios. So I might start with, for example, if I wanted to find x, that is adjacent and the r is hypotenuse. So I might say cosine of theta is adjacent, which is x, over hypotenuse, which is r. And then if you multiply both sides by r, here's your relationship for x that we know. And then I could, of course, do the same thing to get the relationship for y. So those are just from this right triangle that you can draw. So when people get stressed out about memorizing the four things in this box, I would venture to say you probably already know all of them. Okay, so let's use that to convert the following polar equations to Cartesian. You can also do this by checking the graphs of the polar and checking the graphs of the Cartesian and making sure that they look the same. But I think you'll find overall this is not too bad. So we don't necessarily have a relationship for just 2 cosine theta. I cannot necessarily just turn that into x or y. But if it was r cosine theta, then that is the same thing as x. So what I will do is I'm going to multiply both sides of the equation by r, because then I have r squared on the left and 2r cosine theta on the right. And what happens is every time I see r cosine theta, that is actually equivalent to x. Well, r squared is also equivalent to x squared plus y squared, because if you think about that Pythagorean theorem, that's where r squared came from. You can leave it like so. You have actually converted it to a Cartesian. I wouldn't necessarily recommend solving it for y. We should recognize that this is a circle. So I can put this in the form of a circle so that I can see what my center and my radius are. So for example, I could subtract 2x. And then I can complete the square to figure out what the center and radius is. So for example, I'll take this -2 off to the side. I'll cut it in half and then square it. So I should add 1 to both sides to complete the square. And then I can right now have a perfect square, so I can write it in the form of the perfect square. And so this is really, I think, a little bit more usable of a form. Again, both of these should be equivalent, but again, I think one is more helpful than the other because this tells me it's a circle with center 1, 0, right? Because the 1, that's a shift to the right 1. There's no shift to the y. And then it has a radius of 1. And that's exactly what we saw when we graphed this before as well. So some of them that we're going to do don't really require much effort at all. If you'll look at this number 10, I'm still converting this to Cartesian. R squared equals 5. Well, R squared is the same thing as x squared plus y squared, and that equals 5. So this is a circle, right? Center 0, 0, because I'm not shifting left or right at all. We should know transformations. And the radius in this case, square root of 5. Okay. Okay, we talked about r equals, this one is r equals -3 secant theta. Sorry, that secant theta popped up late. I thought it was just -3. If it was just r equals -3, it's a completely different story. So I don't really have anything about secant in my box here. You can certainly transform things so that you do memorize everything with all 6 trig functions, but I'm just going to make sure everything is sine, cosine, or tangent, and then I should be able to work from there. So for example, secant is really the reciprocal of cosine theta. And again, I want things to be r cosine theta or r sine theta. I want it to be written in that form so that I can replace that with an x or a y to go to Cartesian form here. So I see that if I multiply both sides by cosine theta, I have r cosine theta now on the left, and on the right, I just have -3 because those cosine of thetas divide to 1. R cosine theta is x, and so this is my vertical line. Okay. All right, so let's look at r equals, and we'll try to do this without the box being seen, and we'll see if we can get this done. So r equals cotangent theta, cosecant theta. Again, I like seeing things in terms of sine and cosine, so I will do that. R equals cotangent of theta is cosine theta over sine theta. And cosecant theta is the reciprocal of sine theta. Again, I could certainly write sine squared theta, but I don't know if that's going to help us look at this any differently right now. What I'm going to actually do is say, remember, I want this r, since it's not really r squared right this second, I want that paired with either a cosine theta or a sine theta, because then I can change that into an x or a y. So what I'm going to do is multiply both sides by 1 of the sine thetas. Again, that will divide out to 1. So I have r sine theta on the left, which I will absolutely want to kind of leave if I can because that is y, equals cosine theta over sine theta. Now we would think, oh good, cosine theta over sine theta is cotangent theta. Yes, but my whole goal here is to get this into x's and y's, to get this into the rectangular mode, or Cartesian mode, not polar. So you're trying to get rid of all r's and all thetas. Well, I know that for every sine theta, I'd really prefer for it to be r sine theta because then that's my y value. So what I'm going to do is multiply the numerator by r if I multiply the denominator by r. And what you've got to feel a little bit more comfortable doing is sort of manipulating in what you need. So I need r cosine theta or r sine theta, and so find a way to make that happen legally, mathematically. So I can multiply by r over r. That's really just 1. So now I have r sine theta equals r cosine theta over r sine theta. And I can substitute all of those in. R sine theta is y, r cosine theta is x, and r sine theta is y. I can multiply both sides by y. and I have a sideways parabola. Okay. If I wanted some more detail about this, I might say it's a parabola that opens right. So it looks something like so. Okay. All right, so let's look at r squared sine 2 theta equals 2. And let's convert this one to Cartesian. So I do think that, r squared, sure, that's x squared plus y squared. But before you get too carried away with that substitution, because that is correct, you've also got to deal with sine of 2 theta. So if I also have thetas here, I really need to pair up an r with sine theta, and then I can say that that's y. Or an r with cosine theta, and then I can say that that's an x. So I don't want to be too quick to do that kind of substitution. So instead what I'm going to do is say, you know what, nothing that I had in that table talked about a double angle. So I'm going to use my double angle identity and say that this is actually, this is actually r squared. Sine 2 theta is 2 sine theta cosine theta, and this whole thing equals 2. So I can actually divide the left by 2 and divide the right by 2 because those divide to 1. And then, again, I think what we'll get better at the more you do this is seeing that, again, I'm not going to say that r squared is x squared plus y squared, although it is. I'm going to say if I have a sine theta, I need to pair that with an r. So I'll use one of the r's for the sine theta and the other r for the cosine theta. That still is the same thing as the pink line above it. It's just a different way to look at it. And so then r sine theta is y, r cosine theta is x, and that will equal 1. And if you solve this for y, because this does solve nicely, you can divide both sides by x. Again, not to remove x, but just to relocate it, right? I can see that I have the reciprocal function. And so it looks something like so. And there is a vertical asymptote here at x equals 0. Okay? So now let's do the conversions the other way. So let's convert the following Cartesian equations into polar equations. So now I'm going to give you the x and y's, and I want you to tell me the r's and the thetas. So if x equals 7, really every time I see an x, I'm going to think of r cosine theta. Okay? And then the way we type this into our calculator is by saying r equals, so I am going to solve this for r, so I'm going to divide both sides by cosine theta. Again, not to get rid of it completely, but rather just to relocate it. Or you could write this as 7 secant theta. Either way would be fine. Okay, next would be x squared plus y squared equals 4. So I don't necessarily need to say r cosine theta quantity squared and r sine theta quantity squared. I know x squared plus y squared equals r squared. So r is plus or minus 2. Okay, I can type that in here. So moving along, what about a line? Y equals 1 plus 2x. Well, okay. Y we know to be r sine theta. Here's a 1 plus 2, and I know x to be r cosine theta. And I need to solve this for r. So I'm at least going to put my r's on the same side of the equation. So I'm going to subtract r, I'm going to subtract 2r cosine theta from both sides. Then I can factor the r out. And I can divide by what I'm multiplying r by. So sine theta minus 2 cosine theta. So this will divide to 1. So I have r equals 1 over sine theta minus 2 cosine theta. And this does not look necessarily easier than the Cartesian equation. And I understand that because we don't necessarily need polar mode to just graph a line, right? It helps us graph things that are not functions. Well, that line y equals 1 plus 2x is a great function, so I would leave that. And be careful, don't reciprocate individual terms or do anything crazy like that. Just leave it. Okay, so 4x squared equals y. So let's convert this to polar. So again, x is r cosine theta. That quantity will be squared. Make sure you're not squaring the 4 as well. Equals y, which is r sine theta. Okay, so I will square in here. Okay, I can get the r's on the same side of the equation because that might be what you're thinking first. So I will do that. I'll subtract this r sine theta over to the left. If that's what you were doing, make sure you then put equals 0 because you do have an equation, so you need to at all times have a left side and a right side of that equation. Okay, now here's something neat that we can do in polar that we really can't get away with in rectangular or Cartesian. There are an infinite number of ways to write each polar coordinate. So remember, each polar coordinate is r comma theta. And depending on our theta, that will depend on how many times, for example, we've gone around the unit circle. So we can find coterminal angles. So there was a video on that and finding a few of the different representations for that one point. You actually have an infinite number of representations for that one point. So what we're allowed to do in polar that we're not really allowed to do in rectangular is we can divide by r because we're still going to be able to get it back. So, because we have, again, an infinite number of ways to write that polar point. So I'm going to divide the left-hand side by r and the right-hand side by r. So that gives me 4r cosine squared theta minus sine theta equals 0. And now I can see that I probably didn't really have to subtract the r sine theta to the left because I'm actually going to add it back over to the right because now it doesn't have an r anymore. So it'll become positive. So I could have gone right from the green to the blue if I divided by r. And then to solve for r, I'll divide by 4 cosine squared theta. And I am going to rewrite this for you, and hopefully this is going to use your trig but also set you up for success when we do area. So while I could leave this, I'll go up here. So while I certainly could leave this as r equals 1/4 sine theta over cosine squared theta, I am going to rewrite it just to see if this makes sense of why I might rewrite it. So r equals, I'm going to leave the 1/4 as the coefficient, sine theta over 1 of the cosine thetas times 1 over cosine theta. Again, just separating out those cosine thetas. And then that is sine over cosine is tangent, and the reciprocal of cosine is secant. Any guesses why I might like this better if we are heading into areas coming up soon? Well, sure, because I know a derivative whose answer is tangent theta secant theta, right? In other words, I can take the antiderivative of tangent theta secant theta. So it just might be helpful in the future. Again, there's nothing wrong with that up there, but I might do the answer that's in the box, or at least make sure I can, get there. Okay, so let's look at one more here. Square root of 3 times y equals x. Again, this is going to be a line. If you don't recognize it, you could divide both sides by square root of 3, and so it looks like so. Okay, so this is a line in Cartesian mode. So let's convert this. So y equals r sine theta, and x is r, cosine theta. Well, if we're solving for r, remember we said we can divide both sides by r, right? Because we will still have our infinite number of points. Well, if I divide both sides by r, it's actually going to go away. They divide to 1. So all I have left is rad 3 sine theta equals cosine theta. I don't have an r left to solve for. So it should make sense to you now that let's try to solve for theta. So I will, or at least write it in terms of a trig function of theta. So for example, I might divide both sides by sine theta. And so I have square root of 3 equals cosine of theta over sine theta is cotangent of theta. If you're not familiar with that, because I will solve this for theta, you might reciprocate the left and reciprocate the right. So if cotangent theta is square root of 3, I then know that tangent of theta should be 1 over square root of 3, and I can think of what theta gets me to that. Well, I'm just going to look in the first quadrant here because it's positive. And so tangent would be opposite over adjacent. So this is my 1 rad 3 2 right triangle here. And then if I wanted to see a hypotenuse of 1, if that's how you studied these, then there you go, right? Divide all 3 sides by 2. And so I know what that theta is, right? Opposite my 1/2, for example, is always going to be a 30-degree or pi over 6 angle. And so there's my equation for this line, because remember we said if we just have a line with some slope, this case it was 1 over square root of 3, I know my theta is pi over 6. So maybe I could have gone right from the beginning to that, because if the slope of this line is 1 over rad 3, it should make sense to you that that's what I was saying. The tangent of theta should be 1 over rad 3. Right? If I think of slope of the tangent line, I think of first derivative, or I think of the slope being 1 over rad 3, I'm thinking of tangent. And so I don't know if that helps you get from A to B, right? But I can get there regardless, just looking through my polar conversions. So theta equals pi over 6. Now, I know there are 2 triangles, right, where tangent is positive. If you think of all students take calculus, or if you think of just what quadrants, right, is tangent positive in, it is positive in the first and the third. But again, I'm not too concerned with the segment down here in the third, because I could get there if I pair this theta with a negative r. So positive r's will put me in quadrant 1, and negative r's will put me in that quadrant 3. So I will have the whole line, not just half of it. So in closing, I hope that this helps with your converting some of these equations either to polar or from polar to Cartesian. There will be a video coming soon on the derivatives of polar curves as well and what that looks like. I hope you found this helpful.